Swayam Prabha. Digital India. Educated India.
Yesterday, we covered the first 3 chapters from the book that I sent you. I was not presenting any equations or any details. It was mostly overview, how to look at multiphase flow. That's all I was covering. Today, I will start discussing some details. Okay. The first thing I want to do is multiphase flow obviously has lots of particles in there, but let's try to spend this morning just looking at one particle. Okay. So, one particle in a flow. What will be missing is particle-particle interaction, which I said is very important, but we are going to miss that thing to build our sort of knowledge. So, with that, let me also point out that why do we look at a single particle? Because when we do the simulation at the meso scale or at the macro scale, in other words, you are looking at scales much bigger. Therefore, we are not going to be putting a grid around this particle, this single particle. Therefore, if we can't put all the grids, we want to have some formula for the drag. In other words, the momentum exchange, heat transfer between the particle and the surrounding fluid. So, in other words, we want a cheap way of calculating how the particle is interacting and talking with the surrounding fluid. So it's just we are heading towards modeling with the knowledge that we can't put the grid. Of course, if you are doing a particle result simulation, you don't need to worry about this. Okay. So if we want to model the interaction of this isolated particle, one particle with a flow, what do we need? What would such a model need? And that's what I tried to list here. Well, you would need to tell something about the particle, what shape it is. Well, we will mostly deal with spherical, but that's an idealization. Real particles are more complicated. Okay, so real drag loss could be more complicated, but we are going to look at some of the physics for a spherical particle and the size and how fast the particle is moving, both translationally. It could be spinning, because we know that spinning balls can have reverse swing and whatnot. Okay, so it's very, very important. So how it spins, etc. So that describes only the particle. Now we also have to describe the flow. So now you have to think a little bit more carefully. How do we describe the flow? So we all know Stokes drag. When we talk about the Stokes drag, we are not talking about the flow velocity very close to the particle. We are looking at far field. So in other words, you tell the particle and you tell what's the flow, oncoming flow, far field, or technical term is undisturbed flow. So that's this term here. So in other words, all the drag loss will be expressed in terms of particle characteristics, which are listed here, and what the flow would be had the particle not been there. Okay, that's the clear definition of undisturbed flow. Is you have to ask the question, what would be the flow without the particle? Now when you deal with Stokes drag or other classical problems, you don't have to worry about these things, because you are told, okay, a velocity coming towards the particle or the far field velocity, etc. But when you start doing your Euler-Lagrange simulation, in a big complex turbulent flow, lots of particles. Now you have a particle, there are many particles around it. Now the definition of far field or oncoming flow, etc., are not very clear. Therefore, one way to precisely define what should be the flow characterization is, it's hard to do it, but you might want to think in terms of, had the particle not been there, what would have been the flow there. Okay, that's a very clean definition, so that if you know what the particle's characterization, which is its size, shape and velocity, and if you knew what the flow would have been had the particle not been there, with those two things you can now talk about what would be the force on the particle. That is exactly what you would do in a point particle Euler-Lagrange simulation or Euler-Euler simulation. So the first lesson is what is an undisturbed flow. So that's what I covered right now, and a little bit more on that is, basically you have a particle and let's say a uniform flow comes. So u infinity, if the particle had not been there, that would be the flow that would occupy this volume. So whatever the volume occupied by the particle would have a velocity u infinity had the particle not been there. Okay, and that's why this would be called undisturbed flow. Now the particle may have a size, may have some velocity, it may have some angular velocity. So this would be a case of a uniform flow and a particle moving inside that uniform flow. So this will be the undisturbed flow. Now what causes the force on this particle? You can think about it. In this particular case, the fluid has to negotiate around the particle. So you will have a flow like this. If the particle is, suppose, is not moving. So this is what you will call the actual flow, and this actual flow is undisturbed flow plus disturbed flow. If the Reynolds number is small, this the disturbance flow will be the Stokes flow. Okay, there will be a Stokes flow around it. So in other words, the particle tells, hey, I am here, therefore you must obey no slip and no penetration around me, and that creates a disturbance flow. Okay. Now what we are interested in this case is force on the particle. This force on the particle is nothing but integral of pressure and shear stress around the particle. Okay. Now you could take the undisturbed flow, it may have a pressure that could be changing. Say for example, it could be high pressure here and a low pressure here. Okay. So in other words, the undisturbed flow itself could have a pressure variation, could have viscous stresses and so on. If the, in a uniform flow they are zero, but if the undisturbed flow is more complicated, like a turbulent flow or something, even without the particle, in the region occupied by the particle, fluid stress may not be zero, and if you integrate it, there will be a force, and that is called undisturbed flow force. So in other words, this is the force exerted by the particle, not because of the perturbation, because of just the flow being there. Even if the particle wasn't there, even if you replace it with the fluid, that fluid will be experiencing that force. That's there, that's the background force. Now in a uniform flow that's 0 because there is no pressure variation, no. But you have to keep this in mind is that there is undisturbed flow. One easy example of an undisturbed flow is, we all know buoyancy force, right? So when you have a particle in a swimming pool, a big ball, and you just push it down, pressure is increasing, the background pressure, the undisturbed flow is increasing, high pressure at the bottom, low pressure at the top, and is pushing the fluid up. That I will call the buoyancy force is an undisturbed flow force. Okay, it's not because of there is no motion, the particle is not even moving, so there is no perturbation, but you feel that. Okay. Now the disturbance flow is because of the fact that if there is a flow, the flow has to negotiate around the particle, so the perturbation flow creates additional force, and that's where the Stokes drag and other things come. So think of it this way. So the force on the particle will be broken into two pieces. One is the undisturbed flow force, and the other part is the disturbed flow force. So I'm trying to build the story. You all probably heard of Maxey-Rayleigh equation, BBO equation, etc. And I'm going to spend and say a few things. I won't derive this. In the book we have derivation of those things, but we are going to talk about what it means. Okay. So I have said all the things here. So with that knowledge of what is undisturbed flow is and the force created by this undisturbed flow, and then most of our interest is in the what happens in the when the flow gets disturbed, when the flow has to go around the particle. So what I'm going to do in the next 15 minutes is first talk about what is the perturbation flow and in the low Reynolds number limit. I'm going to consider 4 classic problems in the steady Stokes limit. So the flow is low Reynolds number and the flow is steady. The first one is the classic problem, Stokes drag, which is uniform flow over a rigid particle, and you can talk about flow due to a spinning sphere. By the way, uniform flow over a rigid particle is the same as fluid being stationary and the particle moving. They are one and the same because of Galilean invariance. So you can think of the first problem is particle having relative velocity, translational velocity, and the second one is particle having relative rotational velocity. And another problem that is very interesting is because this is what will tell you what happens when there is viscosity, how viscosity changes. You will have to understand when you subject a particle to a strain, how does it change the stress? Okay, the presence of the particle changes the stress, and that will give you modified viscosity. This is the problem Einstein solved. Now all of them, though we will do it for a rigid particle, we could consider a droplet or a bubble. Okay, so you can ask bubble or a droplet subjected to a uniform flow, bubble or droplet spinning, bubble or droplet in a straining flow, etc. Okay, and I won't go through all those details. So these are the preliminary information. So these are all, one way to think of them are models. These are models for force on the particle, droplet or bubble in the low Reynolds number limit. Okay, so I know these are classic problems, so I wouldn't worry about this. Now, so what we have done here in some sense is our fluid is very simple. In the first 4 problems, either it's a uniform flow or it's a vertical flow or it's a simple straining flow. But in reality, when you are doing Euler-Lagrange simulation in a turbulent flow, the undisturbed flow at the particle is going to be way more complicated. Okay, so what do? Now in the 0 Reynolds number limit, there is this Faxon's theorem which allows you to get rigorous answers for any complicated flow. So we will say, I will say one slide on that. So, at least in the 0 Reynolds number limit, Stokes limit, how can we handle much more complex flow? Okay. So, obviously, this is not going to cut it for turbulent flows, because there the Stokes limit is not appropriate, but let us start learning what that is. Now, what happens is also is that when you start making the problem unsteady, okay, even in the Stokes limit, you have to worry about other forces. So far in a steady flow, you only have what are called quasi-steady forces, a steady force. Now, when the particle is moving or accelerating, not moving, just you have to change in time. Okay, the relative velocity must change over time. So either the fluid is accelerating or the particle is accelerating. Okay, when the problem becomes unsteady, then you have a much more complex problem. And the last bit, which is the Maxey-Rayleigh-Gatignolles equation, puts these two complexities together, which is we are in the 0 Reynolds number limit, Stokes limit, but we are talking about a particle seeing a complicated spatially varying flow and changing over time. Okay. Now, in reality, you will have to also go to finite Reynolds number. So, even at the one particle level, modeling forces is very complicated, okay, let alone multi-particle interactions. Okay. So, but I want to build that machinery in this lecture, and then, like I said, we will then talk about finite Reynolds number. Now, there are a lot of models there. I won't be able to cover everything, but my job, like Professor Pushpavanam said, is to highlight some of the things that people have worked on and people are currently working on, and so on and so forth. Okay. So the Stokes solution, I hope all of you know how to derive that. So the Stokes solution gives force on a particle to be 3 pi mu of the fluid, diameter of the particle, and it's a function of u minus v. Now, I will put here a superscript on. Okay, I will use different terminology. So what we are talking about is, hey, if I know what the undisturbed flow at the particle is, and I know the particle characteristics are like diameter of the particle, this is the particle velocity, and the relative velocity will give you, so this is a model. This is a model where you don't have to resolve the flow around the particle, you don't have to put it, but as long as the Reynolds number is very small, this works. Okay, this works. By the way, one thing I want to emphasize, that this is a vector relation. In other words, you have the relative velocity vector, and that is used to get the force vector. Okay, and they are in the same direction. So that's what the Stokes drag is saying. Okay. Now, quickly let me just show what would be the result if you had a droplet or a bubble. So in this case, instead of a rigid particle, you have a droplet or a bubble. So this will be the extension of the Stokes drag. Okay, now written in an index notation, and here I am using 0 particle velocity, the droplet velocity. So I'm just assuming the droplet to be, or a bubble to be stationary, so there is no v of I, the droplet velocity is 0. Therefore, this is for a stationary droplet being subjected to some velocity, and you may have studied that there will be flow inside the droplet, and that flow is called the Hill's spherical vortex. Okay, so as the flow goes around it, there will be flow circulation inside the droplet. So there will be fluid going round and round, and therefore this outside flow is not being asked to be no slip. It cannot penetrate. We still assume spherical droplet. So this problem also can be solved, a little bit more complicated. So you have to solve the Stokes flow outside and the Stokes flow inside the droplet, and you have to do matching on the surface, and the notes are given there. But this is the final answer. This is the final answer, and it only depends on the viscosity ratio. So mu that appears here in the numerator and the denominator is the viscosity of the particle, or the inside viscosity divided by the outside viscosity. Okay. So, if that viscosity ratio goes to infinity, that is a rigid particle, so inside one does not move. If that viscosity ratio goes to 0, that will be a bubble, and some other problem you will have constant. So I have written what the answers are for a bubble. Okay, the coefficient changes, and this is for when the viscosity ratio is 1. Okay, so these results are sort of classic results. Now I said that we are going to look at sort of survey some of the results people know from low Reynolds number theory. This is the another problem, which is particle subject, in this case it is a quiescent fluid, the fluid is not moving. So you just have a particle, and the particle is spinning with angular velocity omega, and therefore the particle set the fluid also spinning. Okay. So here again you can solve the problem. So this is the steady Stokes equation, and you subject it to far away boundary condition, and on the particle you subject the fact that the particle is rotating. So these are straightforward things. So you get the solution, the flow field. I did not say in the previous case for a uniform flow going over a particle you have classic solutions of Stokeslet and a doublet. Okay, so those are very important quantities, but for a rotating case you will get what is called a Rotlet. Okay, so these are fundamental solutions of Stokes flow, so perhaps covered in your fluid mechanics graduate level fluid mechanics course. Okay, so you can calculate the stress distribution, the tractional force on the surface of this particle, and you can integrate, and finally this is the result. A spinning sphere has no drag, obviously, there is no flow direction, but it has a torque, and you have an exact relation for the torque on a sphere. Okay. Now, so we have covered a uniform flow going over a sphere and a rotational part. In the 0 Reynolds number limit, these solutions add. So if you have a flow with a uniform component and some rotation, you can simply add them. The other thing that you can talk about is what happens if you have a particle subjected to a straining flow like this. Okay, this is a pure straining flow, and you know that this velocity gradient tensor in this case is symmetric. Okay, so you can call it symmetric strain rate tensor, and it will result in a stress field, and the stress strain relation gives you viscosity, right? So what we are talking about is what happens if you put a particle in there and how it changes the stress field. Again, I will not go through the details, so this problem is also fairly easy to solve in the Stokes regime, and the solution is a little complicated, and I said that I won't go through all the details. And important thing is that the flow caused by the perturbation flow caused by the presence of the particle creates what is called a stresslet. So what we have so far covered is that for a uniform flow you have a Stokeslet and a doublet, and then for a rotating problem you get a Rotlet and you get a stresslet. So this is how the perturbation flow caused by the presence of the particle in varying ambient flows in the Stokes limit. Okay. Yeah.
Can you explain those four things, the Rotlet, Stokeslet, a bit more in detail? For some of them, they may not be aware of it.
Yeah. Yeah, I can do that, but then I will not move forward. See, that's the problem. So I said that maybe they can, if they are interested, it's all in the notes. Okay, and they can catch up because they don't need to know all the intricate details. That I wanted to bring people aware. I know that some of you may not have studied low Reynolds number fluid mechanics. That's okay if you don't know. What is it?
This happens at very creeping flow condition.
It is creeping. Everything is 0 Reynolds number, not even low Reynolds number. You're right. It's 0 Reynolds number limit. Creeping flow solutions. Okay.
Just briefly,
What is that?
briefly just tell 1 or 2 points.
Oh, not. Okay. It's basically one way to think of this is if you put a particle in creeping flow, very low Reynolds number, all we are talking about previously I said, what did I say? I said if you know the undisturbed flow, the presence of the particle will change the undisturbed flow. Why does it change it? It changes because on the surface you demand the velocity to be no slip and no penetration. So you must add a perturbation to the undisturbed flow and the sum will satisfy no slip and no penetration, right. So the question is, what people have done is that if I stick in a particle in a uniform flow, in order to satisfy no slip, it will create what is called a Stokes flow, which is the sum of a Stokelet and a doublet. Okay. Now the Stokelet is nothing but response to a point force. So in other words, if you take a fluid and apply a point force, the flow that is created, the Stokelet will look like this. My drawing is pretty terrible. So in other words, if you take a fluid and apply a force F, point force in a viscous fluid, what will be the flow? And that is the Stokelet, and by itself it cannot make it captures the drag on the particle, but it doesn't capture the whole story. It won't make. So you add on top of it a doublet, and a doublet is nothing but, I don't know whether you have studied in potential flows. You may have studied a potential doublet. So a source and a sink, they are so close to each other and it creates a doublet. So the doublet flow will look like this. So one way to think of this is you take the uniform flow, this one, and you add some of this Stokelet and some of this doublet, and you add all of them, it will be the solution to Stokes flow solution when there is a particle. So in other words, the solution to Stokes flow is nothing but a sum of these things. Now the Routlet is very simple. Routlet is nothing but fluid going round and round. So Routlet will be is simply, since the particle is rotating, it will make the fluid go round and round, and the circumferential velocity will keep going down. At the surface it will be the same as the particle, but as you go to infinity, that circumferential velocity will go to 0. Stresslet, I don't know how to draw it. Okay,
That's what I wanted. Whatever you told me, that's fine.
yeah. So stresslet will be a little bit more complicated. So the beauty is that all we are saying is that there's a lot of work people have done trying to understand and categorize, represent in simple way what happens if you stick a particle in a flow. Okay, that's what we are here, right? What does the particle do? So by doing this, why do we need to know is that they are easy way of calculating how the particle and the fluid interact, and you can quickly get what the fluid does to the particle, what the forces exerts. We saw the Stokes drag, we saw strain field. Now what I am trying to do is, if you stick in a particle in this flow, now in this straining flow, there will be no drag, okay, because there is no net force. It just fluid is coming this way and going the other way. So there is no force, no torque. So what does it do? Okay, so a straining flow will not create any force or torque, but it will change the viscosity. So again, I don't want to go into the details. If there was no particle, this would be dissipation, right? You know, dissipation is nothing but 2 times viscosity of the fluid strain field, which is a symmetric tensor, dyadic double dot product with itself will be the definition of dissipation. So, this would have been the dissipation if you did not put the particle, but if you put the particle you can calculate the dissipation, a new dissipation. We have a slightly modified flow and you calculate the dissipation, and a little bit of work. Why does something dissipates? If the dissipation increase, that means your viscosity has gone up. Okay. So, you can calculate the effective extra dissipation due to the particle. So, this comes out to be the extra dissipation because the particle had been there. So, now there is no drag, no lift, but you see when a particle is subjected to strain, the stress strain relation will change. You will get extra stress created, which means the particle makes the fluid behave as if it has a slightly higher viscosity. Okay. And that is what yesterday I was talking about, is the thermodynamic effect and transport effect. Now, the same thing I can do for conduction, the heat. So, in other words, if there is a thermal gradient and I can ask, if I put the particle, how much heat transfer changes, and that will give you how the conductivity of the fluid, just like viscosity of the fluid now is changing, the conductivity of the fluid will change. So, that has been extremely exploited because nanoparticle suspensions are used for enhanced heat transfer. Why? Nanoparticles will change the relation between thermal gradient and heat transfer. Here stress strain relation changes, the same way temperature gradient and heat transfer changes. Okay, that is a very interesting problem. So, here just for one particle you can calculate this. The details are not that important, because even if I talk about that you will forget it very soon. Okay, it is all in the notes, but the take home message is much more important, and the take home message is that presence of particle changes the stress strain relation, and that change is parameterized in terms of increased viscosity, and this is the relation. This relation is by Einstein. When he was in his early 20s he wrote this. Okay. He derived this and he said that phi here is the volume fraction. So, he said if you have 10% I am sorry 1% volume fraction, phi is 0.01, and your 5/2 is the coefficient that sits in front. So, this formula is not correct, it is only good for low values of phi. Okay. You know exactly how the mixture, so mu m is mixture, though we solved only for one particle. What Einstein said this, if there is a dilute, particles are far away, so each of them going to increase viscosity locally, and what is the net viscosity of the mixture. The net viscosity of the mixture comes out to be viscosity of the raw fluid plus 2.5 times volume fraction of particles in that. Now, this probably is good for maybe a couple of percent volume fraction, and beyond that it will not be good, and exact similar equation exists for thermal conductivity. So, if we are dealing with problems and viscosity of suspension will be higher than that of a pure fluid, and sometimes you may have to take care of it. Okay. So, this is something that I wanted to summarize.
So, question in that, when we are talking about that, is it the net effect of the fluid that is having a greater viscosity, or is it?
It is this, yeah. So, suppose you have a plate, chemical engineers, many of you would know this rheometer of some sort, and you fill the fluid and you pull this plate U, you are applying a strain, shear strain, and this is how you measure the viscosity. If you had pure fluid you would get mu f. If you put particles in there, you have to apply a higher force to move it the same thing. So, in other words, the effective viscosity of the mixture has changed, and that was given by this formula. So, this is the effective viscosity of the mixture. Okay. Now what happens is at the level of micro scale, each particle is creating a stresslet. Every particle is creating its own stresslet, and you add them up, they all increases the viscosity, and that's why the stresslet is a very simple solution. And this works only when the particles are far away, and therefore good. When particle volume fraction increases, then it gets very complicated. So the same thing people have done for bubbles and droplets. Now a bubble or a droplet subjected to a strain field will also change the stress strain relation, but since the bubble is now can move, in other words there can be fluid motion inside, how it changes is different, a little more complicated to solve this problem, but you can solve it. In fact, in the book you can look at problem 4.8 where you can look at the details, but the net effect is what is very interesting. Is you have a precise expression for how in these particles, instead of being rigid particles, that was the previous slide, if they all are tiny little bubbles or droplets, you use this relation and you will get your modified viscosity. And there is a similar relation for conductivity, thermal conductivity, where you will have to worry about the conductivity of both the liquid, the droplets, as well as the, the surrounding fluid. Okay.
Sir, yes. So if you have a we have a bubble and a drop, but inside bubble there is a compressible volume. Yes. But the effective viscosity of in both the cases will be same.
No, even if you ignore, this is all a great question. This is all assuming the particle, the bubble or the droplet are not very compressible, they remain spherical, etc. When the sizes, the actual droplet problem could be much more complicated because they can become elongated and so on and so forth. So this result that's in this slide is a very simplified assumption that they all remain spherical, they are very small. Okay, in that limit this result applies, and then the volume doesn't change due to compressibility, etc. Now people have done tons of work. I mean, there's like zillion papers on this topic. So somebody would cover how if a droplet changes to an ellipsoid or when it becomes compressible, what the answer, they are in the literature. This is just the tip of the iceberg, some simple way of thinking what happens. Okay. Any other question?
I think so. If the gas bubble remains spherical, can you still use the Einstein's relation for the correction of the viscosity?
No, I would use this, not Einstein's. Einstein did it for the rigid particle. So what he did was his stresslet is for a no slip boundary condition. This problem that you see here, you are slipping, the fluid outside is slipping and there is some fluid motion inside the droplet. So somebody has sat down and solved that problem and they summarize the result in this beautiful formula. Only assumption they make is that droplet and bubble is of a fixed size, okay, and it remains spherical, no deformation. So this is exactly summarizes what I've said before. Particle, when it's subjected to a relative velocity, well, you have a doublet and a strokelet and there is a drag force. Okay. Particle, when it's subjected to a rotating motion, if you are inside a vortex, then particle will tend to get a torque and it will also try to spin. All these cases you can see that particle is being forced to follow what the fluid does. If you subject the particle to a uniform flow, there is a drag wanting the particle to move fast. And now there also you saw that there was a time scale, tau p will tell how fast it will catch up. Now for the rotational problem there is a time scale and they are related. How fast, if you stick in a particle in a rotating flow, how fast it will catch up and start rotating with the surrounding fluid. Once you start going with the surrounding fluid, no more torque. Okay. And the last thing is if you subjected a particle to a straining flow, it will create a stresslet and it will increase the viscosity. So, those are the 3 simple lessons. So, why this problem? Well, the way I have broken this problem, you can see that if you have a particle and you have a complicated flow coming towards it, okay, you can do a Taylor series expansion of the undisturbed flow. You see the terminology I use for undisturbed flow. I is just an index notation. So, you can take what we are asking is, hey, I remove this particle and there is a flow coming. How does this particle behave at the particle? So, in other words, what does the undisturbed flow look like at the particle? Then to the leading order, it's a uniform flow, and then you can do a linear. This is the first term of the Taylor series, and there are other terms in there. So, if you do a Taylor series, now in a 3 dimensions, because it's a vectorial Taylor series. Now, what you find is that the gradient of the velocity will come, and the gradient of the velocity can be broken into a rotating part and a anti-symmetric part and a symmetric part. The bottom line is that to the leading order, any particle you can think in terms of being subjected to a uniform flow plus a rotating flow plus a straining flow, and we know how all 3 of them work. Okay. The good thing about the Stokes limit is the answer for this problem and the answer for this problem. This gave Stokeslet and a doublet, this gave a Rotlet and this gave a stresslet. You can simply add them. You cannot do that at finite Reynolds numbers, but at 0 Reynolds numbers. So, now we have a much better knowledge of the Stokes limit. A particle subjected to a fairly complicated flow, you can just take what happens to the uniform part, what happens to the rotational part, what happens to the straining part, and you add them and you get everything. Okay. So, now, I will not go into details, so I want to go a little bit more. So, there is a reciprocal theorem. I don't know, I want to skip all these things. The question that we are asking, this guy Faxon is an amazing guy. Okay, he wrote 3 theorems and he solved the problem in some universal way. Okay, and I am going to talk about one of his theorems. Okay, what Faxon said in the previous problem, I said, hey, if you have a complicated Stokes flow, let's Taylor series expand and look at just the uniform part, rotational part and straining part. And Faxon said, I don't need all those things, give me any complicated flow, I really don't care, as long as the Stokes number is 0, the Reynolds number is 0, we have the solution. So, what he did was, you could have eddies coming, very complicated flow, but usually unfortunately the Stokes flows are not that complicated. Okay? But nevertheless, his theorem, the first law, is amazing thing. He used the reciprocal theorem that I skipped in the 2 things, and he proved this formula. What he said was, let me write it again here, is the force on this particle is equal to, now it's written, it's 6 instead of 3 because I write it in terms of radius of the particle. Previously I wrote in terms of diameter of the particle, which is the same. Now, the question is, if you think in terms of Stokes law, since the particle is not moving, here we are talking about stationary particle, you will put fluid velocity here, right? You will put the fluid velocity, a vector quantity. Now, I ask you a question, what is the undisturbed flow? What will you put? If it's a uniform flow, you know the value. But let's say, let's take a very simple example. Let's erase all these things to make it a little bit more. Let's say we have converging flow. A particle, fluid lines. Now, what velocity will you say this particle is subjected to? I mean, it's changing. In other words, the velocity the undisturbed flow velocity. In other words, you take the particle, so you have the undisturbed flow at the particle is changing. Okay. If the particle is really, really tiny, you may say, who cares? But if the flow changes on the scale of the particle, then if somebody tells you go use the Stokes law, then I will be puzzled. Another example I will tell you, a very simple problem. Let's say you have a particle and a shock coming towards it. Here velocity is 0. Here people denote it as u2, post-shock velocity. And let's say the shock is right over the particle. Okay, let me erase this. And the shock is just happened to be on the particle. And I ask you, what will you put if you want to use Stokes drag law? What velocity will you put there? Not very clear, because half the particle is 0 velocity and the other half has 500 meters per second. So in other words, when you think in terms of Stokes drag, etc., lots of drag relations that we use, keep in mind that we are talking about undisturbed flow seen by the particle, and that could change on the scale of the particle. If the particle is small compared to how the turbulent scales are, then who cares? The whole particle stays the same velocity. On the other hand, the other extreme of shock particle interaction, fluid velocity changes so rapidly. In other words, the thickness of the shock could be 50 nanometer. Even a micron sized particle looks too big. Okay? So in other words, everything is relative. Okay? So the main point I want to talk about is, when velocity changes on the scale of the particle, what to put? Do I put the velocity on the left or the right, at the top or the bottom, or just simply calculate it at the center? Most people just use the center velocity. Now I tell you, that's disastrous for, in some times, for a shock particle interaction. Okay? For example, if you take the shock to be out here, it hasn't reached the center of the particle, you may think there is no force, because the fluid velocity at the center of the particle is still 0. But the front guy is being slammed with the flow and is already seeing tremendous force. So you just can't use central velocity at the center of the particle. So having said that, I have made a case that, well, particle velocity, fluid velocity, the undisturbed fluid velocity, I am not talking about the disturbed fluid velocity, undisturbed fluid velocity, in other words, the velocity of the fluid in the absence of the particle, could change on the scale of the particle, in which case Faxon said, I mean Faxon's law won't work for shock particle interaction, unfortunately, because there the Reynolds number is too large. Okay? But he said, when velocity changes on the scale of the particle, his brilliant relation was, and his exact solution, he said that just take this velocity, undisturbed velocity, and average it over on the surface of the particle. Okay, that was the Faxon's first law. So in other words, if you have a converging flow like this, and you want to calculate the, you just average. Oh, I can't use the pen right now for, but what happens is that you have to calculate you take the undisturbed flow and you do a surface average. So for example, in the case of the shock particle interaction, even as the flow comes towards a little bit, the front side of the particle is now has non-zero velocity, back side has 0 velocity. You do a surface average and you will get a force, and you will get excellent answers. Okay? So it turns out that even though Faxon did not derive this for anything but 0 Reynolds number, the results are so brilliant that it seems to hold and work very well. So this is something for you to think about. If your particles are big, or the flow changing on the scale of the particle, Faxon theorem is really good. Okay. So this is the result interpretation for Faxon's law is very simple. What Faxon's, one way to think of this is, Why a surface average, you may think? Well, what does the particle do? It makes the velocity everywhere on the surface go to 0. Undisturbed flow is coming. What does the stationary particle says? Every point on a surface tells the fluid stop, 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 stop. Therefore, Faxon's law now makes a lot of sense. You say, well, you integrate over the surface, and that's the kind of velocity the particle is stopping. Okay, and therefore a very simple interpretation. So he said it's 6 pi mu f times radius is the same as Stokes' drag law, except don't use the center line as center velocity, use the surface average velocity, and it takes care of any kind of flow variation. Okay. Yeah.
What should the layer which should be averaged? The layer that should be averaged. What should be the?
Yeah, no. Why do you worry about the layer? Remember, when the particle is there, there is boundary layer, all sorts of stuff happens. We are asking you to average, surface average, the undisturbed flow, the flow that would exist without the particle.
But let's say I have a radius of 1 centimeter. So what thickness should I take to which I should average?
Exact surface average.
Okay.
Why do you have to have any thickness? In fact, if you have a non-spherical particle, you just go around the surface of the particle without any layer and you average the undisturbed flow on the surface.
The surface average of the undisturbed flow.
Absolutely. Because remember, we never deal with the perturbation flow. This captures the effect of the perturbation flow only in terms of the undisturbed flow. See, what we want is what's the effect of the perturbation flow? And the answer is, well, don't worry about the perturbation flow. Just look at what flow was coming and I will tell you the force based on that. Because the drag law, that's the most important thing in a drag law. It tries to account for the perturbation flow without knowing the perturbation flow. Right? When you do an Euler-Lagrange simulation, you only know the flow that's coming, okay? And you say, I have an undisturbed flow. Had there been a particle there, what would be the force experienced by the particle? So you take the undisturbed flow and you do a surface average, okay? And he has the same. His theorem 2 and 3 will discuss the torque and other things. So he basically tried to solve the Stokeslet, Rotlet, and Stresslet problem for any flow, and those are the 3 theorems. So whatever I said before, he tried to give answers for a very generic case. Okay, so that was my first lecture.
So, sir, one question.
Yes.
So, like some microbes, they have cilia, they are moving. If we are knowing average surface velocity, we can solve for fluid velocity also, right?
Yeah, you could do that. You could do that. So, if the surface is moving, then it induces a flow around it. So, in the Stokes limit, there is a lot of interesting things. So, mostly what I am talking about is not, I mean, the kind of stuff that you're talking about, the Marangoni effect, cilia, things moving around, or surfactant effect, they really make the problem much more complicated. And I'm no expert in that, so I'm mostly dealing with droplets, bubbles, and sort of particulates. Okay, so the problem could be made much more complicated.